We start with the equation of a simple harmonic oscillator, x double dot plus x equals 0. You might recognize this as the equation for a linear spring, and we can re-express it as a system of equations. We know about solutions to this particular equation, or we should. They're of the form x of t equals a cosine t plus b sine t. And this can also be written in another form. It can be written in the form r cosine t plus some phase offset, and we can use a trig identity to see that this is true. So the expansion of t, the cosine of t plus phi, gives us this cosine t, cosine phi, sine t, sine phi, and from this we can relate r cosine phi to a and r sine phi to b and solve for r and phi in terms of a, b. Specifically, r squared is a squared plus b squared, and the tangent of phi is negative b over a. But now imagine that we don't actually have a perfect linear spring, and instead, whatever our implementation is, our spring or our oscillator is a little bit imperfect. It's a little bit nonlinear. And I say a little bit because this epsilon is very small. It's close to 0, and so we say this is a weakly nonlinear oscillator, and that's because h is some nonlinear function, but epsilon's really small. It's just a small perturbation from the simple harmonic oscillator that we were working with before. Solutions before were of the form x of t equals r cosine t plus phi. So y of t, which is the derivative of that, would be r sine of t plus phi. And if we draw these in the phase plane, we expect to just be going around circles. And so we expect solutions of this thing to, I don't know, be perturbed from that in some way. Say a little bit off from the solution that we had before, but not too much off. And the amount off is going to be a function of epsilon. And I want to note that if h is just a function of x, then this thing is going to still be conservative, and so this epsilon h term is going to cause some kind of distortion to what were perfect circles. Maybe they're going to be a little bit oblate. And in the case where h does actually depend on x dot, that should actually be a y, right? That's not an x dot. That's a y. In the case when h depends on x and y, we expect either, okay, now maybe we have a little bit of friction attenuating things, and so we'll get a very slow spiral inward that will look a lot like this oscillation for a long time, but is very slowly spiraling in. Or maybe if the sign is the opposite of that, we could get a spiral outward that was also very slow. Or potentially, actually, we could end up with a limit cycle appearing, so that also happens depending on the type of the function h. So I guess we have kind of like 4 basic possibilities that are going to happen. We distort slightly our nice conservative orbits. Our orbits are no longer conservative, and we either have a stable spiral because the physics intuition is that this is some friction, we've added some friction, or the sign is the opposite, and so instead of adding some friction, we actually inject energy, or somehow it works out so that the friction and the amount of energy injection work out to give us some kind of stable limit cycle. This perturbation to an equation for which we have a nice solution begs the question, how do we figure out what happens in the perturbed case? We have our solutions to the original equations. Those were the unperturbed equations. And now, as we think about the perturbed equations, we know that whatever x of t and y of t are doing, it looks a lot like this. They still spend around 2 pi going around the circle. They're at a similar radius to what they were before. They have a similar phase to what they were before. So to understand the perturbed equation, let's just say that the solution in the perturbed case have some x and y behavior, and we don't know exactly what it is, but we know it was similar to the simple harmonic motion we saw before. And let's define a new function. It's called r of t, and it's just going to be defined as whatever radius this thing has as a function of time. And we know that because of the perturbation, before our radius was constant, but now it's probably changing in time, and the way it's changing is going to depend on epsilon. And in addition, we can choose some phi that depends on t as well, and it's chosen so that however phi depends on t, it's always being given by the actual perturbed relationship between y and x. Previously, in the unperturbed case, this phi would just be a constant, but now y and x don't have quite the same relationship they did before, and so we're compensating for that by letting the phase change a little bit over time. So given these definitions for r and phi, we can say that whatever the perturbed x and y are, we've defined these r and phi so that this is true. This perturbed x is equal to this perturbed r times cosine of t plus this perturbed phase, and this perturbed y is equal to this perturbed r times sine of t plus this perturbed phase. So now we know basically 4 things about the solutions of the perturbed system. We've defined an r and a phi that are changing in time, so that whatever trajectories of the perturbed system are doing, they have these solutions. In addition, we know that the perturbed system satisfies these equations, and so we can combine all this information to find equations for how r and phi are changing in time, equations for r dot and phi dot, and these equations will allow us to figure out what kind of perturbation we have to our original nice motion at a fixed radius. How is our progression around the circle being adjusted, because phi can slow us down for a little while and then speed us up and then slow us down and then speed us up, and r can cause us to wobble in and out. And so we want to know what are these 2 functions, so we're going to find differential equations to help us figure that out.